In recent years, many museums have adopted augmented reality technology to provide more immersive experiences for their visitors. However, AR is less frequently leveraged by those who create the exhibits. Our work explores how AR can assist conservators and historians with sculpture conservation. After importing an AR replica adjacent to the physical sculpture, our method employs two different forms of physical analysis. A static analysis derives the tipping vulnerabilities of fully connected, homogeneous sculptures from their base geometries and mass distributions. On the other hand, a dynamic analysis uses real-time physical simulation to report tipping behavior of non-homogeneous sculptures in response to a user-controlled collapse. After the collapse, this method visualizes the ground impact severity across the sculpture surface. We have implemented this method as an iOS application using the Unity engine and ARKit. Formative user studies with conservators from the Museum of Fine Arts in Boston evaluate our techniques and provide valuable insight for future research. We test our method on digital reconstructions of various pieces from the Museum of Fine Arts. We supplied photographs taken from a variety of view angles to Agisoft Metashape, which uses photogrammetry to generate sufficiently detailed and texture-mapped 3D models. The models were then manually post-processed in Maya to remove artifacts and make appropriate separations for widely propagated cracks. To import a desired AR model, we require the user to place two reference points on the physical sculpture, indicated by the thumbnail labels. These reference points provide enough information to generate the corresponding model adjacent to the physical sculpture, with matching scale and rotation. After the import and alignment process is finished, the user can visualize all the possible tipping directions for the sculpture. Objects tip over by hinging around the edges of their convex hull base. As a result, each edge of the sculpture base corresponds to one tipping direction. Each tipping direction has a critical angle, which represents the minimum angle that the sculpture must rotate in that direction before it will collapse under gravity. We indicate the vulnerability of each tipping direction with a color scheme, where red represents the highest vulnerability. Photogrammetry artifacts can often produce extraneous edges on the sculpture base, which can be hard to manually smooth out before running a stability analysis. We have developed an edge clustering algorithm that consolidates a sculpture's base geometry in real time, providing an uncluttered interface while still preserving the most important tipping directions. Here we show an example of a base graphic without edge clustering on the left, as well as the same base graphic with edge clustering on the right. Here's a short demonstration of a static analysis on one of the sculptures from the Museum of Fine Arts in Boston. Notice how the sculpture's base graphic aligns with the user's current perspective of the AR sculpture base. In the dynamic analysis, the user starts by tilting the ground until the top segment of the sculpture falls over. This occurs at an X angle of negative 13.5. Then the user is able to visualize the ground impact severity. We approximate widely propagated cracks with a planar slice through the sculpture. This allows our dynamic analysis to simulate each sculpture segment separately. Feedback from the conservators was largely positive. They believed it could supplement current conservation methods at large museums by exposing vulnerabilities that may not be visually intuitive and may require additional investigation by a structural engineer. At smaller museums with limited resources, it could potentially play a larger role. A few of our necessary assumptions affect the accuracy of certain sculpture conditions. For sculptures with highly erratic cracks, our planar crack approximation would attribute inaccurate volume to each partition, affecting the mass distribution calculations. We also don't yet account for artificial supports placed by the conservators, such as bolts and armatures. For future work, the conservators requested that we convert our user-controlled ground rotation angles into automated behavior that simulates realistic scenarios, like earthquakes. Additionally, we aim to add customizable pedestal geometry to both of our analyses. Finite element analysis would help us predict crack behavior as a result of internal stresses, especially as the sculpture distributes all of its mass onto a single base edge during tipping. On the other hand, a fracture analysis method could help predict cracks that are likely to form as a result of ground impacts,